Howdy. Howdy. So I'd like to introduce our seminar speaker this week, Soutir Bandapadhyay. Sorry if I got that wrong. He's an associate professor in the Department of Applied Mathematics and Statistics at the Colorado School of Mines. Before joining Mines, he was an assistant professor in the Department of Mathematics at Lehigh University and a visiting scientist at the National Center for Atmospheric Research, or NCAR. Most importantly, though, Soutir earned his doctorate in statistics from Texas A&M University in 2010, so he's an Aggie. His research interests include developing novel inferential procedures under spatial and temporal dependence and investigating their asymptotic properties. And he has applications in climate, which is what we'll be seeing today, environmental studies, finance, and biomedical studies. He also works very closely with Doug Nitschke, who I invited to speak here in 2 weeks. So we'll see if it's a different talk.
Yeah, there is a high chance that it's going to be the same.
Don't really tell Doug if it's the same talk. Okay? He's also an elected member of the International Statistical Institute, and a recipient of the International Indian Statistical Association Young Statistical Scientist Award. So let's welcome our speaker.
All right. Good morning, everyone. And thanks, Trevor, for this introduction. As he has already mentioned, that I am an Aggie. I graduated in 2010 under the supervision of Dr. Lahiri, Dr. Shoman Lahiri. It was a long, long time back. Most of you probably, I mean, if the number, if 2010 doesn't make too much sense to you, I was here when Dr. Simon Suder was the department head, Dr. Michael Longmaker was the director of grad studies, and most importantly, that was the time when we were part of the Big 12 conference, and we used to lose to Longhorns almost every time. I mean, it was a disaster. Every time we used to sit in front of the TV during the weekend with the hope that this time we will win the game. Every time it was a disaster. So that was the time. And last time I was here in probably 2012 or 2013. And so I'm here after approximately after 12 to 13 years. And last night I was just driving around this area and I saw a lot of changes in College Station. I mean, it's unbelievable how all these things have changed. We used to see the student housing. It used to be called Hensel Apartments. We had a lot of friends over there. That's gone. I don't know where it is right now, but it's completely gone. And I'm staying in a hotel. I think it's in that neighborhood. So yeah. So that's the thing. With that, okay. So let's come back to this. The talk, the title of this talk. So as you know that I'm going to talk about the high resolution long-term weather data for energy. Now, before we get into the details of this talk, let me give you some background on this, how this project started and everything. So we all know that our future climate is uncertain, right? We don't know what's going to happen, but given years of observed climate and weather patterns, and due to the development of different climate models, we now can, to some extent, we can make projections about the future climates, right? So in the last several years, due to these greenhouse emissions, etc., we know that the global surface temperature is changing or is going to change, and it has been given a lot of publicity. But it is also known to us that the other properties, other atmospheric variables, for example, the cloud patterns or the aerosol properties, those variables are also going to change, or the properties are going to change. As a result, it's going to have some impact on the future solar radiation. So the local companies, or the federal governments, they use, I'm going to talk about a database, which is called the National Solar Radiation Database. I'm going to give you some details about that data set. But typically what they do is that they take that data set and they based on the data, they try to project the future solar radiation. And based on that, they decide where to put the future, solar facilities or the PV facilities, right? The problem with the current NSRDB data set is that whatever they are projecting is based on the historical data. So they are essentially not capturing anything which is coming from the climate models or the climate change. So a few years back, some scientists from National Renewable Energy Lab, that's a DOE funded lab, they came to us and they said that, okay, this is the problem, and you guys work on climate models or climate related stuff. So we would like you to work on this and see if we can project the future solar radiation based on the regional climate model output. So that's the, overall view of this project. That's how it started. There are a couple of things. The first thing is that I'm going to talk about a very small part of the project. I'm just going to look into a very small section in California, okay, just to show you that how this methodology is working or how we develop the methodology. But the whole project was to come up with an efficient, explainable algorithm which you can which can be used or which can be implemented for the entire CONUS or contiguous United States. So of course there could be we can do a lot of sophisticated statistical modeling in this particular area. I'm sure we can, but at the same time, remember that every week we had to talk to the scientist, right? And we had to explain them what we are doing. So it was essential for us to stick to some basic models, right? Instead of looking at very complicated, sophisticated models. So that's one thing. And yeah, and as I mentioned before, the second one is that I'm basically going to give you an overview of what we have done. I'm not going to get into too much mathematical or technical details. I just want to give you the idea what we have done. And if you feel that something can be done after that or it can be improved, please feel free to talk to me. I will be happy to talk to you about this. And maybe we can work together on those kind of things. All right. With that, the next slide is this one. So this is completely orthogonal to my talk, but I thought that I should mention this to my slide, or at least spend one slide on this. So I'm part of this organizing committee for this ENVR 2024 workshop, and it's a biannual workshop, and it's happening this year. It's going to happen in the MESA lab at National Center for Atmospheric Research in Boulder, October 3 to 5. Great place, great time to visit Boulder, right? During that time. So if you are already aware of that, great. If you are not, especially the grad students or the postdocs, if you really want to learn more about environmental applications and build a network, talk to different people. I know that a lot of you are working on environmental problems. So this is a very good place, a great place for you to visit and meet some professors or your peer group in this kind of workshop. All right, some funding acknowledgement. As I mentioned before, that this was supported by DOE, and this is a collaborative effort between a group of scientists at NREL and Colorado School of Mines. Here is the list of all my collaborators, but you can look at all of their names, especially Tagnichka, because he's coming in 2 weeks, and I hope that he's not going to talk about the same project. So I need to remind him that, look, Dad, I have already talked about this, so make sure that you're going to repeat this whole thing again. But I would like to say that I would like to mention Maggie's name here, and she's currently a fourth-year PhD student, and she's going to graduate this summer. She basically has spearheaded this entire project from the very beginning. You know, as an advisor, we used to have weekly meetings. We used to give her a lot of ideas, but at the end of the day, she was the one who implemented everything and came up with all this modeling techniques or the methodology. So yeah, I thought that I should definitely acknowledge her effort here. Okay. Now the next slide, I'm going to talk about the National Solar Radiation Database. But before that, okay, so I have until 12:30. So can someone tell me like how it works? Should I keep like 5 to 10 minutes towards the end? Is that how it works? Okay. All right, yeah, so this is the solar radiation database. As you know, I have already told you that National Renewable Energy Lab, it is situated in Golden, and it's a DOE-funded lab, and one of their major contribution to the energy community is to create and maintain this NSRDB, this database. All right, and what they do is that they you know, it's an open source database, very rich. And of course, if you have already developed a methodology and if you are looking for a big data set, this is something you can definitely explore. Okay. What they do is that, or the local companies or federal government, they take this data set and then they use this data set to predict future solar radiations in places, right? So that they can decide whether they are going to have consistent or increasing amount of solar radiation in those places. Based on that, they are going to put the solar facilities or the PV facilities in those areas. So here are some details. It's, as I already told you, that it's a very rich database. It is 4 kilometer by 4 kilometer resolution, right, at a spatial scale, and from 1998 to 2014, and hourly and 30 minutes temporal scale. Okay. So far, what it has been doing is that it is typically using a physical model without doing any making use of any statistical model. It is solving some numerical PDEs, some computer models, some physical models at the surface, and based on different kind of observations to create a gridded data product. Okay? And we know that we might expect that solar radiation will change in future based on the climate change. Okay? So what's our goal? Our goal in one line is to characterize the distribution of future solar radiation at the same space and time resolution as NSRDB under scenarios of climate change. That is something that is the main contribution of this work or of this project. Okay? So when I say that we are going to characterize the distribution, what I mean is that we are going to come up with an ensemble, okay, of possible outcomes. Okay? So I guess that this term ensemble is familiar to many of you, but in case you don't know this, I'm going to spend some time on this because I can see a lot of grad students and junior faculty members. If you are unsure about how this works, it is essentially the statistical ensemble of possible outcomes we typically come up with if we have any physical model, underlying physical model. The physical models are usually very time consuming and expensive to run, right? So what we do is that we try to come up with a statistical emulator, okay? The emulators are cheap to run, right? And at the same time, it's going to give you some, you know, it will quantify the uncertainty in the projections, future projections. So what it does is that the statistical emulators, they typically give you a bunch of observations, a bunch of fields which you can expect to see under the same scenarios, right? So it's kind of all of those are essentially, you can say that those are equally likely set of possible outcomes coming from the same process. Okay. And the good thing about this ensemble is that since we are going to use some statistical emulators, it's very easy to run. It's cheap. I mean, you can run it in your computer using any R package very fast, and you do not have to store any results, any number, right? You can create the ensemble on demand, or the members of the ensemble on demand. So this is, I'm pretty sure that you all have seen this picture. This is a very popular picture. I took it from Heskey's book, but I thought that maybe this is a good example where I can explain what this ensemble, how this ensemble looks like. So I have taken 6,000 samples of handwritten digit 6 from that book. Yeah, that's the plot, and this is the mean across all of those samples. And if you look at the first 20 members, those are looking like this. So you can say that, okay, these 20 members are kind of the members of that ensemble. You see that each of them are slightly different from each other, but all of them are coming, you can assume that all of them are coming from the same distribution, because if you take the mean, it is going to give you number 6, right? Approximately number 6, right? So that's the idea of statistical ensemble. And of course, ensembles are useful to represent variation in complex objects, right? If you want to figure out some characteristics of a distribution, you can simply calculate a lot of members in that ensemble, and based on that, you can look at the mean, median, percentile, whatever, or any quantity related to that distribution based on that those ensemble members. Okay. What is the variable we are going to talk about? The variable in this project we have 3 variables where we worked on. The first one was GHI, the next one was temperature, and the third one was wind speed. But just for simplicity, I'm going to skip to my discussion. I'm just going to skip to this GHI, or global horizontal irradiance, that index, and temperature and wind speed are kind of very similar methodology-wise. Of course, we need to make a little bit tweaks here and there for different variables, but overall, if you think about the overall methodology, they look pretty same. So what is GHI? This is a nice plot to show what this GHI is. This is a combination of direct horizontal irradiance and DNI, which is the direct normal irradiance, times cos theta. This theta is called the zenith angle. Okay, so you can see that this GHI is essentially a linear combination of these 2 components, right? DHI and DNI. So now the statistical problem we started with is the following: what will GHI look like in future years with a changing climate? We need to come up with a gridded data product for GHI for future. Okay, here is the workflow for modeling solar radiation or for this project, right? There are a lot of steps. I'm going to talk about each of them one after another, but the very first step would be the regridding step. All right, so usually, think about the RCMs. The RCMs are usually they give you the daily values, the daily average, right? And also they are at 20 kilometer, usually at 20 kilometer by 20 kilometer grid. So definitely there is a mismatch between RCM outputs and the NSRGB output, right? So the first thing is that in order to build a model based on RCMs and to predict the future solar radiation, we first need to bring everything down to the same level. So our first step would be to regrid the RCM projections from its native grid to the 20 kilometer NSRGB grid. Okay. Now, once they are on the same grid, right? Then I'm just going to fit a simple regression model, right? Where Y is our NSRGB output. On the right-hand side, we have a multiple linear regression model with different RCMs, right? And that will give us the predicted observed GHI based on NSRGB. So that's going to give us a model how to predict the future values. That's going to be the first step. The next step is the downscaling part. Because remember, NSRGB, the ML wants us to downscale it at 4 kilometer by 4 kilometer spatial scale and hourly or 30-minute scale in the temporal side. So on the temporal side. So that's the second step. Once we have the NSRGB data set at 20 kilometer level, at 20 kilometer by 20 kilometer grid, at an hour, sorry, at a daily level, then we have to do temporal disaggregation. From daily average or daily total, we need to bring it down to hourly scale. That's the first step. Also, from 20 kilometer, we need to go down to 4 kilometer or 8 kilometer, right? That would be the spatial downscaling part. Is it clear? Any question until now?
What is RCM?
Oh, the regional climate models. So basically, this we have in climate science, we have a lot of regional climate models. Every country or every continent, they have their own RCMs, and these RCMs are essentially they try to predict the future climates. Okay, and they solve a lot of, again, numerical PDs and everything. It's not a statistical model; it's more like a numerical model. And based on that, they predict the future climate. Okay, it's a good question. Any other question? Yes.
Downscaling from 20 kilometers to 4 kilometers.
Of course, yeah. I'm going to talk about that. I'm just saying that this is the workflow. This is what we need to do. I haven't talked about how we are going to do that. Yeah, that's part of this talk. Okay. So the first step is the regrouping step. Okay. So here is a plot where you can see that the native grid of this is, I think this I got it from the WRF, the Weather Research Foundation grid. Okay. So this one, the blue dots, those are, sorry, the blue plus signs, those are the native grid. So those are essentially the actual RCM grid. Okay. And the blue dots are the NSRGB grid. So the first step would be to go from the native grid to the target grid. Okay. Now, how can we do that? Very easy. We can just click, right? We can use clicking, right, to go from one grid to another grid. So that part is easy, and that's what we have done. But what we have, we were deliberate to check if we are doing this regridding, there should be some uncertainty involved in that, right? And whether that uncertainty will have any downstream effect in future downscaling or disaggregation modeling activity, right? So that is something we wanted to know. So that's the nice part about this first problem. In climate science, people always do this regridding using kriging. There are a lot of other different ways to do regridding, all right? But they never consider the uncertainty due to this regridding step. They always take it for granted. They say that, okay, we are doing regridding and then let's work with that. But what will be the effect of this regridding? They never talk about that. So we thought that maybe it's a good first project for Maggie, where she can check whether this regridding will have some effect on future projections. So just to give you another perspective, on the left-hand side, we have the regional climate model grid, and as far as I can remember, it is coming from the WRF model. And on the right-hand side, we have regrouped that to the target grid, the NSRGB database. And to see that it's still overall capturing, it's capturing the overall structure of the process, but of course, we can still see some differences here and there due to the uncertainty. And by the way, here we have done this rigging based on just usual kriging approach, the simple kriging method. Oh, kriging is best linear unbiased prediction in spatial data analysis. So let's say you are given a sample in a domain, in a spatial domain, and you want to predict the process at a new location, and you typically want to predict that using the best, you use the best linear unbiased prediction. So in spatial data analysis, we have a peculiar name. It's called kriging, and that's after Daniel Krieg. He invented this method. That's why we call it kriging. Okay. All right. So I have already talked about this. This is going to be the framework. So I'm just going to run a simple multiple linear regression model where our response is going to be the NSRGB data. Now you see that all of them are on the same grid, right? So we can run this model. But the problem here is that if you look at those RCM1, RCM2, and RCM3, these are the three different RCMs we have taken. I did not put too much details on those RCMs here, but we considered the Canadian regional model, the CRCM5, and WRF. These are the three models we considered. Okay? And we also took care of some, we also consider some seasonality in the model. So if you just look at this model, it seems like it's easy. It's a multiple linear regression model. But what we wanted to know is that now, due to the regridding, all of those RCMs will now have some uncertainty, right? So it is no longer a simple multiple linear regression model. I mean, the climate scientists, they have been using this multiple linear regression model without acknowledging the fact that due to regridding, there will be some uncertainty. But we wanted to be a little bit deliberate, and we wanted to check whether it will have any downstream effect. So with that, so what did we do? I'm coming to the next slide. I'm really nervous about the next slide, and I'm going to tell you why. Yes, Shamiran, yes.
So why are you interested in estimating those beta 1, beta 2, beta 3?
Very good question. Just give me 1 minute, and I will show you why it is interesting to estimate those betas. First of all, you see that here all of those RCMs and NSRGB are on the same spatial grid, right? So this is essentially going to give us a model which will tell us that, okay, if I have the RCM outputs, I can use the RCM outputs, which is going to tell us how the future climate is going to be looking like, right? And based on that, I can predict the future GHI values.
So in future, you do not have NS or DB values?
We don't. That's the idea, right? Because we want to predict the future values so that ML can use that, or DOE can use it for siting future solar facilities, right? Yes.
How many RCM values you are using?
For the model, how many outputs are you?
So RCMs are on 20 kilometer by 20 kilometer grid, right? On a daily scale. And I believe that in this model, we are taking, so we are looking at the overlap of all of this database, right? NSRGB, RCM1, RCM2, and RCM3. And I think the overlap was in between 98 to 2008 or 2009. Yeah, I think so. Okay, so 11, 12 years of data. All right. So what we can do, I mean, from here, once we have all this regret data, we can, what climate scientists do, we can just use, in R, we can use the LM function, right? And we will get the estimates of betas, right? And that's where we are not considering anything about the regression uncertainty. The next slide I'm going to show you is a little bit of Bayesian twist to this problem. Now, that's why I was telling you that I'm feeling nervous because I know that we have a lot of people here who are experts in Bayesian, and I do not want to, I mean, it's a disclaimer. I should make a disclaimer here that it's a very naive Bayesian model, which I'm going to show you. Of course, we can do much better than that. But the idea was just to see whether, our Bayesian approach is doing better than the frequentist version. The Bayesian version will have some prior data, right? Or some prior information. And we wanted to know that whether we are doing something better than that. So here is the Bayesian version, and most of you will laugh at me that, okay, what is this going on? I mean, we are doing so many, sophisticated Bayesian models, and we are talking about this basic stuff. This is probably, we all learned this in, Math 303 or Math 201, right? So what we are doing here is very simple. We are conditionally simulate each RCM onto the NSRDB grid. So are you familiar with the term conditional simulation? Okay. By conditional simulation, we mean that based on the observed data, we are going to simulate the process at a new set of locations. Now, the constraint here is that if some of the new set of locations coincide with the actual locations or the observed locations, then the simulated process, the simulated data will exactly have those values. So it's not going to predict the observed values. Okay, so that's the difference between conditional simulation and unconditional simulation. By unconditional simulation, you are given a data, you fit a process, you estimate all the covariance parameters, and then based on that, you simulate. And there is no guarantee whether, the simulated data, if at any point, it will have the same value as the observed one. But by conditional simulation, we try to constrain that. Okay. So we are conditionally simulate each RCM onto that MSRDB grid. And then for each simulation, so we have 100 conditional simulations for each RCMs. And for each simulation, then we are making several draws for beta and sigma square. So, once we have the conditional simulated values or, process, we can use that in our linear model, and we can do some Bayesian, we can look at the posterior distribution of beta and sigma square based on that. And we can take several draws from that posterior distribution. What we wanted to do is that we wanted to check whether the 95% confidence interval, which is coming from the usual LM function in R, which is very simple, with ignoring all the regression uncertainty, will that be different from the 95% credible interval, where we are now looking at the conditionally simulated data set, which in turn will give us some uncertainty, or which will capture the regression uncertainty. Okay. So this is the same thing in a little bit more mathematical way, but now I'm coming back to your question. So you see that the very last line, beta hat weights RCMs and deviation from 1/m. So if you are dealing with, let's say, in this particular problem, we are working with 3 different RCMs, right? So we can expect that all of those RCMs are going to be, they are going to have same weight in predicting the future. And if that is not, then it will tell us that there is some bias going on in those RCMs, and we need to fix that. We have a lot of small things we had to tweak, but I'm just going to give you the overall picture in this work, what we have done. We also looked at, instead of the original data set, when we were fitting the model, we were looking at the log linear transformation. And this is the function. So what it is doing, you can see that usually the mean, the cutoff, the threshold, it is set at a very small value. For example, in this work, we took it as the 10th percentile of the observed data. And it says that if U is large or anything above that cutoff, it's still going to give you a linear function. So you can still explain everything in that linear world. And when it is small, when x is smaller than the 10% quantile, then we are making this log transformation. And the reason why we wanted to do that is that to constrain the regret value to be greater than or equal to 0. Because when we were starting, when we were trying to do the regrading without any constraints, it is possible that some of the solar radiation values become negative. And it is not possible, right? The solar radiation cannot go below 0. So we had to put this constraint. All right. So here is the output, or here are some results. As I've told you before that we are just looking at a very small region in California to build a model. And once we build the model, we give it to NREL, and they are using HPC, and they are doing all this sort of things to implement that at a higher scale. So that's not our business. I mean, Maggie is working with the NREL scientists to do that, but I don't get too much involved in those parts. But here, this is California, and I'm picking this point here. Yeah? And what it is showing you is the following. So I'm just, we ran this LM function, we looked at the 95% credible interval, and you see that things are not, I mean, let's not worry too much about the intercept, because this intercept can be different for different reasons, and that will be our next topic, or that will be our next subject of discussion. But just if we look at CSCM5 and WRF, these are the two regional climate models, you see that these black dashed lines are the posterior 95% confidence interval, credible interval, and this magenta pink lines, dashed lines, those are the usual LM, the output we are getting from LM function, 95% confidence interval, a prediction interval. Right? And they look pretty similar, right? They are very, very similar. So with that, we decided that, okay, that means that at least for this particular application, this reading does not have too much downstream effect. But now we have a methodology, we gave it to NREL, and in future, if they want to work with a different data, they can still fit this model, and they can check whether the reading will have some downstream effect in the future projections. But at least for this particular case, we did not see any much difference. And of course, if we don't see any too much of difference, it's always better to stick to your usual LM function, right? Because you do not have to do the follow-up, posterior distributions and all those things. So that's where we ended. Some results. First, we looked at the average bias by location. Okay. Again, the same region, California. We were looking at the small box in California. How did we calculate the average bias? Now, I'm probably abusing the definition of bias here, but what we have done here is that we have this beta hat coming from LM function, and we have those beta hats which are coming from all of those posterior draws, right? So we are looking at the difference between them, and we are taking average over all of those values, okay? Just to see that whether the frequencies and the Bayesian versions, they match, or whether they are different or not, okay? And you see that intercept and the CSCM5, this is the RCM we have. The values are very, very small, right? here for Weather Research Foundation, the WASP model, we can see some bias here, right? But still, it is not that significant, right? We also looked at the out of sample prediction or out of sample property of this new model. And what we did is that we looked at adjusted R square, right? So we hold out year 2010 from NSRDB dataset. We build our model as you were asking me that what I think we took 1998 to 2009. We build our model based on that dataset, and then we try to predict the 2010 values, right? And then we matched whether it is matching with NSRDB, the actual observed value at NSRDB. And you see that the adjusted R square, it is fluctuating from 30% to 60%. Okay? And so this is the coastline. If you go inside, it's not bad. It is giving us almost 60% of adjusted R square value, so which is kind of a reasonable value. But of course, along the coastline, we have some problem, right? And it is a well-known fact that along the coastline, you have a lot of non-stationarity happening, and it is very difficult to capture everything, you know, with 100% accuracy. So it was not shocking for us that we could not capture the coastline values. But overall, if you look at this plot, it's not doing that bad. All right. We also looked at the out of sample coverage in May, in the month of May, and you see that we have values ranging from 0.91 to 91% to 95%. So which is pretty reasonable, I would say. Yeah. So that's where the first topic of discussion ends. Do you have any question before I move to the next one? It has different steps in this entire thing. All right. Yes, sorry.
You're not doing it hourly.
At this point, we are not doing hourly. But it's a great question, and that's the second project. That's what we are going to talk about. What we are saying is that right now we have this the daily averages or the daily totals, and we are trying to model the daily totals. The next step would be to disaggregate it to hourly scale. Of course, and I'm going to show you how we are going to handle that. We have a diagonal pattern, right?
It seems that the radiation is sort of horizontal from 0 to 0, like percent. Like it will have, and you seem to try to address this with your non-linear transformation.
Yeah.
I wonder whether that's the transformation of the thing.
So we got rid of all the zeros. I mean, we looked at in UTC scale, everything was on UTC. And on UTC, I think we looked at from early morning to dawn. And we did not worry too much about, the values at night, because as you said, that all those values are going to be zero. So we did not consider those values in building the model. But still, I mean, yeah, sorry.
It's a radiation.
Yeah, exactly. We could do GLM, absolutely. That was one of the things we also thought about. But yeah, I mean, you're right. GLM would also be a reasonable assumption or a model to fit. I'm not arguing with that. I'm not saying that that is not another route. Okay. Yeah, good. Yeah. All right. So here is the summary. So RCM is not at the same grid. So we had to regrid, and we were a bit deliberate to understand whether the regridding uncertainty will have any effect in future projections. And finally, at least we concluded that at least for this particular data set, for this particular problem, regrading does not appear to inflate the uncertainty. Okay? And this was Maggie's first project, so we wanted to stick to very basic things, and it got last year it got published in ASCMO. It's a scientific journal which they consider statistical methodology or statistical development in climate science. All right, the next step would be the bias correction. Now, in climate science, people always do this, right? And the reason why is that we have different regional climate models, we have outputs, and often we see that the regional climate models, they have systematic bias in their outputs. And that could be due to different reasons, because it is essentially running a large-scale computer experiment, and it's giving us all the numbers. So it is possible that there is some amount of systematic bias present in those for a particular variable. And what climate scientists typically do is that in order to do the bias correction, they make use of a method called quantile mapping. Okay, and it's very simple. What they do is that they look at the observed values, they look at the modeled values, they look at the QQ plot, and they try to model the QQ plot either with a spline or with a straight line. And with that, they then try to back transform the values, which will have less bias. Okay. That's basically what we have done, but I thought that just for completeness, because someone might think that whether we did any bias correction or not, so I just wanted to make sure that we did bias correction, and we just fitted a smoothing spline to the QQ plot, and then based on that, we predict the quantiles or for the RCM values. So this is the last slide for bias correction. I don't want to spend too much time on this bias correction part. So you see that on the left-hand side, we are essentially looking at the QQ plot, and then we are fitting a smoothing spline. We are back transforming the data based on that, bias correcting the data based on that. And if you see that on the left, on the middle panel, we have the observed process, and after bias correction, we get the rightmost plot. And you see that mostly they are looking the same, but here, these two parts, these are kind of very different, right? So at least we can say that the bias correction is making some difference in the covariates, in the RCM outputs. Okay. Now, let's move on to, sorry, what happened? Okay. The downscaling part. Think how much time do I have? I'm not going to go up to 49 slides, so don't worry. Those are some extra slides. So don't get nervous. I will be on time. All right. So here, before we talk about this temporal disaggregation and spatial downscaling, I would like to show you a couple of pictures just to understand the logic behind this entire methodology, right? So here I have picked 3 different points, right? One is on the west coast, east coast, and one location is in the middle. Okay, and I think it's in April. In April, for a few days, we looked at the observed GHI. All right. Now, what do we observe from here? Of course, we see a strong diagonal pattern, and that is pretty obvious, right? It should start at 0, and then it should go up, and it should reach a maximum, and then it should go down. And after some point, it should be equal to 0. And noise can occur throughout the day, right? Or in some situations, we can see that the noise is only before noon or afternoon. Okay? And of course, the clear sky days have no extra noise. So if you look at the dotted lines, those are essentially giving us the clear sky days, the GHI values coming from the clear sky days. And those values are given to us. That is, the MSRDB database has those values. So that's kind of a benchmark we have. Okay. So what are our goals? We want to create explainable, efficient algorithm, right? We need to explain it very easily to scientists, and of course, it needs to be efficient because at the end of the day, we need to implement that on the entire United States or at a global scale. All right. So that's the first thing. The second thing is that we will be doing the temporal disaggregation. We need to align the hourly data with the number of clear sky hours. So in every day, as I mentioned before, that you have seen that there were some days where some noise was there, before noon, after noon, or throughout the whole day. So we need to align to those things, right? And finally, we also need to incorporate the spatially and temporarily correlated cloud patterns. Okay. Now, here is the diagonal template model. Again, I don't think Dr. Shripara will be very happy with that because she wants to do something more, something nicer than that, but it's a very easy template we work with. So don't worry about this function. What we have done is the following. So look at this. So we try to capture the mean template, okay? And this is a spline function, but it has 3 parameters. I would say 2 parameters, and I'm going to say why it is just 2. So you see that we have beta, alpha, and tau, right? And beta is essentially controlling the peak of the day, right? Of the GHI. Of course, every day the peak will change, right? It's not, you cannot expect that every day the peak will be at solar moon, right? So that beta is a variable, and it will control that thing, okay? That peak. This tau is going to control the length of the day. And again, the length of the day will be different for different locations. All right, so these are the 2 important parameters. The third parameter we have here is alpha. I should not say alpha is a parameter because alpha is already known to us. What it is doing is that it is controlling the height of this curve. But if you look at this alpha is daily total GHI, and it's already given to us, right? We already know what is the daily total GHI, right? Our target is to, so we already know what is the area under this curve. We need to, disaggregate this, this whole thing into hourly scale. All right, so we did nonlinear discourse. We used some nonlinear discourse technique to estimate beta and tau. And then we plotted the data for one particular day in October, I think for a few days in October, and you can see that it is capturing the overall structure quite well, right? I mean, the mean structure. But still, we have some fluctuations here and there, and we need to capture that as well, right? So, what should we do? We looked at the SVD, the singular value decomposition, and we just looked at the principal components, and we saw like how these principal components are behaving. So we fitted the mean model, we looked at the residual process, and that's what we are doing with the residual process. It's not with the actual process, okay? So for every location, for a fixed location, we have a 24-column matrix. So we have the hourly values, and we have as many rows as we have for the days. And then we look at the SVD, a singular value decomposition. So let's see what's going on here. If you look at this, you see that if I go up to 4th order principal component, then we are capturing almost 80% of the total variation. So now if you add more and more, it's probably going to get better, but it's adding a little bit of noise, right? So we wanted to stick to the up to 4th order principal component, and here these are the basis functions of the of this 5Js. But most importantly, if you look at this plot, I don't know whether it is you can see it very clearly or not, but what it is telling us is that if you add one or first two or first three basis functions or principal components to the just a template to the mean function, then how things are changing. And you see that this gray curve, we have a gray curve here, that's the mean template. And as we are adding those principal components, it is gradually getting very close and close to the observed pattern. Okay. So we looked at the weights. By weights, we use the UJs, right? So if you go back, I already told you that we have taken J to be equal to 4. So we only move up to fourth order, the first four principal components. So we have U1 up to U4. And for two different locations or two different regions, the top panel is giving us U1 up to U4. And for another different region, the lower panel is giving us those four coefficients, right? And clearly you can see that those U's have very strong spatial correlation. And that is not very shocking because, of course, we know that the solar radiations in nearby places, nearby locations, they should be similar to each other. And if two locations are far apart, then they should not matter too much, right? The solar radiation can be different. So that's exactly what it is telling us. And we ended up fitting a spatial model for U coefficients to get a smooth surface. And we already stored all these basis functions. So we have the basis functions, we got a smooth surface of UJs, and based on that, basically we can get the value for any random location. Okay. Now, a few more slides and I should be done. So I would like to show you what are the simulated cloud patterns. Okay? And you might say that, okay, what are we doing here? We are looking at 19 April, 3 p.m. We are starting at 3 p.m. and we are going down to, let's say, 24. So 22, 23, 24. Yeah, so 12 p.m., right? So these are all in UTC. And so just -7 from all of these hours, right? So in California, these are the simulated cloud patterns. These are the simulated US sky days. So it looks like it is working well. And we also simulated a time series for these two locations. I mean, I'm just showing you for these two locations. Of course, we have done this for the entire California. And you see that it is very similar to what we are expected to see, right? Finally, this is the conclusion. We have successfully downscaled the daily average to hourly average. We are seeing that this method simulates spatially correlated cloud patterns. And we also looked at different metrics. We haven't talked about, I did not want to include all those metrics and everything, but we looked at all these matrices and those are, I mean, the method is, in general, it is working pretty good. Okay? And this method is currently being implemented on the CONUS or contiguous US. So with that, I thought that maybe I will have some time left and I will talk about something else, but I'm going to stop here. That's all. Thank you.
I think we have time for one, maybe two very quick questions.
Yes. Okay.
So what kind of seasonality variables went into the first model? So I assume the regional climate models have seasonality in them.
Exactly. So I do not remember what seasonal variables we included, but I do remember that we figured out that the seasonal variable is not significant. So we did not, build a model based on seasonally, including any seasonal variable, because as you said, that the RCMs they already have those seasonal structures present in the data set. So yeah, so at the end, we started with 3 different RCMs and we dropped one. I think we dropped the Canadian one and we worked with CRCM5 and WRF. And we also dropped the seasonal variable because those were not significant. Yeah, thank you. That's a good question. I should have mentioned that before. Thank you. Yes.
The past correction seems very interesting that you are using Q2 plots, then back transformation. So is there any name for this type of bus correction?
It's called quantile mapping. Now, I don't know in statistics if there is any name. There might be something. But I am not, it's in climate science, it is called quantile mapping. So if you search with quantile mapping, you will see a lot of, in Google also, in Wikipedia, you will find everything about.
For this type of data, so like your data are being generated from the model, right? In
Right.
RCM.
Right.
So is this quantile mapping advocated for this type of data or any other type of?
Anything. Right. Yeah. It's a very strong approach, I would say that, yeah. So we are just matching the quantiles to do the bias correction. And it has been in climate science for maybe last 50 years, I don't know, even more. So it's pretty common in climate science.
All right, let's thank our speaker.
Thank you.